What is going on, everyone? So today I'm going to be doing a tutorial for how to make a 1206 footprint. And if you've heard me mention before, maybe in that Altium tutorial, that it's important to know how to make your own footprints, or at least understand how they're made and be able to edit them in Altium. Because that way you can curate your own libraries, and I think it leads to a very clean looking PCB design if you have like a nice, like well organized and uniform looking set of footprints for like all your resistors and capacitors. It can even help whenever it comes time to validate your circuit, because you can add in some special marks and stuff like that to make it easier for spotting components. But anyways, we'll just get into the example I have prepared for us. So I just went and pulled the data sheet for a resistor with a that is the size 1206. This is just a generic Vishay data sheet. So typically what companies who make resistors will put on their data sheets is they make one data sheet for like a bunch of different package sizes. So if you even see here in this table, they have listed 0402, 0603, all the way up to 2512. So because resistors are so simple and you can fit all the necessary information within a few lines, so they just kind of save space. It makes it also easier because you only have one document to refer to. So as per usual, like understanding how to read data sheets is also pretty valuable here. Like you don't want to have to read a 10-page data sheet every time you want to make a footprint for a resistor. So figuring out the valuable information out of these is something I guess I'll just go over. So usually, I literally, since I'm only looking for the footprint, and again, whenever you get a lot of practice with these, you'll get used to how different companies lay out their data sheets. So I know like Vishay typically puts like their footprint stuff at the bottom. So here we'll just go to the bottom. Now, say you need to read some information from stuff up here, then it's good. It's a good idea to like understand. Stop and read this every once in a while and understand. Like I know this is like I'm familiar with what this table does, and if you need me to find some other type of information, I could quickly find it on this data sheet. So I'm not instructing you to neglect every other part of the data sheet. Just understand which parts are important for what you're trying to do. So in this case, we're literally only trying to make a footprint. So let's just scroll down to will be like the mechanical information section of this data sheet. So right here, we'll actually scroll below it. So yeah, so there's no more information pertaining to footprints beyond this part. So here we have two graphics. The first one is going to be, this is giving you like a mechanical description of the actual component itself. So say you're trying to make a 3D model or something like that, you would use this information up here to do that. And then below it, we have the solder pad dimension. So this is the actual footprint information that we're trying to get. So again here, in the interest of being like concise and efficient with their data, they have one diagram, but then they have a whole table referring to these dimensions depending on which package size we're using. So because I'm already familiar with like the part numbers and stuff like this, then I know this one right here is because it says 1206 right here. And if you read up in the table, it tells you what the part numbers actually mean. So I know we're going to be using the information in this row of the table right here in order to create our actual footprint. So clearly here on the diagram, it shows that we have a pad that is Y by X. And this is in millimeters. Now it gives two different sections. One's for wave soldering, one is for reflow soldering. Now, I'm not an expert on by any means on the actual manufacturing process, at least yet. So understanding why you would use something, why you would use reflow soldering in one instance and why you'd use wave soldering in another instance, I think that might have to do something more with component placement order, because I know one of these soldering methods, I don't think you can use it if you have certain components already mounted on the board. So just depending on something like that, you might have a hard time using it. To be honest, I don't actually know if you can't physically use like reflow soldering after you've done something to it. But anyways, what I'm saying, we'll make a pad that looks like it can kind of accommodate both of these like situations, I guess. So we'll try to pick something that's a little bit in between both of the dimensions they list. So for the Y specification, it says we have 1.4 millimeters. And then for the Y specification here, we have a huge difference, which is 1.05 millimeters. So right in between that, that's 1.225 millimeters. So we'll pick something around there. Well, honestly, I think since what we could do is, I don't think reflow soldering. Here's what I'll say about this. I don't think it's going to hurt a reflow soldering process if the pad is 1.4 millimeters, right? But it might affect it, the wave soldering, if it's below 1.4. So let's just go with the bigger one. I think that's actually probably a safer bet. So let's just go with, make it 1.4 millimeters by 1.95 millimeters. And just make sure you know that in Altium, these dimensions are reversed, that this is left and right is the X and up and down is the Y. So going forward, so we know 1.4 millimeters by 1.95 millimeters. So we'll just go right in here. We already have pulled up. This is just a little demo library I created before the video. We'll hit place and we'll go pad. Boom. So maybe you remember me giving this little explanation where you're probably worried, like, this looks nothing like what we're trying to get it to do. So you want to come over here. First thing we'll modify is the shape, and it's going to be rectangular. Then the next thing I want to modify is the layer. So up here it has multi-layer selected. We want to just do top layer because this is a surface mount component. Designator is 1. This is important to get this right or have this make sense. A lot of times I like to use numbers. You can actually name these anything you want, but the important thing, the designator is used to sync up this pad to a pin in the schematic. So whenever you make connections on the schematic, it knows like pin 1, aka pad with a designator 1 is what's connected. So that's why it's really important to get those right. Electrical type doesn't really matter. None of this other information seems that important to me. Pad size, obviously, I don't know if this is pad. This looks like it might be pad size. Let's just, yeah, so this is actual pad size. I'm gonna hit Q on my keyboard in order to change this to millimeters. So we have 1.06 millimeters is the X dimension. I think it was 1.4 is what it said. And then what was the Y? The Y dimension in Altium. So it's 1.95 in the vertical direction. We could say that 1.95. So here, if you see this little purple, see if I can highlight it. This little purple box here, which is around the edge of this pad. So this is what is known as the solder mask expansion. So if you've heard me mention it, maybe I mentioned one before, but I'll keep repeating this so that way you can just get it in your head every time, over and over. So think about maybe that, I don't know if you've seen, like, you've probably seen it in movies, maybe you've done this before, but you put like a face mask, you know, for your skin, and it's supposed to be on your face, but they put the little cucumbers in your eyes. So think of the solder mask as sort of like a face mask for the board. It's put on there to protect all those sensitive components under there, and kind of well, it's to protect, you know, from the elements, you could say. It's to protect that precious copper that's underneath the solder mask from the external elements, make it easier for the solder to find its way to the correct location. So much like an actual face mask in real life, we want to have some holes in this actual face mask, so like where your eyes, so you can see, on your nose so you can breathe. You don't want to get any in your mouth because that would just probably taste really bad. So basically the way these things are created is these little purple squares are what tells us where our eyes, nose, and mouth are on our PCB, if that makes any sense. So wherever these purple squares are, it's telling us leave a space in the solder mask for this pad to be there so we can actually solder onto it. We need a hole there is basically what it's saying. We can talk about, and this will probably get more into PCB design rules, but how do you actually know how big this purple box is supposed to be? And that really depends on a few things. It has to do a lot with the manufacturing process. Like, some manufacturers can get this really, really tight, because maybe in a perfect world, you would say keep this tight, make it 0, right? Make this opening only the size of the actual pad. But in reality, the manufacturing process isn't perfect, and that could just lead to a decreased yield in boards where they don't always, when they don't get this process perfect, they have to toss the board, and that just leads to an increase in cost, right? So having a more relaxed constraint on this value can still lead to an effective design, but it will just cost less money, is kind of what I'm getting at. But yeah, so don't worry about this, just leave it as the default, because it works just fine. especially for designs that we're doing right now, it's totally fine here. So we have this board, or we have this first pad already completed. It's the right size. It's good to go. So we're gonna head Control C, Control V, and we're just gonna paste it over there. And the first thing I want to do is make sure my designator is correct on this. Okay, so basically it's literally, because it's an exact same pad copy, so we know that because I mean that's like it's gonna have the same properties, except for it's gonna have the designator of 2. Hope that was obvious why we copied it. So the next thing we want to look at in the data sheet is the actual pad spacing between each pad. So if we look here, this figure G here is the pad from inner edge to inner edge, and it tells us that in the table. And however, what we're trying to do in Altium, what I found, it's really easy if you go from center pad to center pad, because the Altium software you can literally hit like edit set reference, and you do pin 1 and it just locks onto the center of pin 1. So with that in mind, it would be much easier if we could figure out how far the centers were from each other, and we can do that with a little bit of math, right? So we know from edge to edge is the length G, but how far is center to center? Well, we know from edge to center of this pad is G plus 1/2 Y, right? Hopefully that makes sense. Whenever we want to go halfway is going to be the center of this pad, so 1/2 Y. Then we know from this edge to the center of this pad is another G plus 1/2 Y. So just only count G once, of course. I hope that makes sense. But then you should figure it out that it's the center to center is G plus Y. So when we look down here, and let me see, G looks like it's very close to the same size. So I mean, we could pick something maybe a little bit. We'll pick something roughly in the middle. That way, we're trying to kind of accommodate for many different like cases here. And that's another thing too with footprints is companies will make components that can sort of like be fit into many different footprints. It's not like it's like a Cinderella shoe type of scenario where you have the exact footprint to fit the exact component. Like you can have a little bit of wiggle room with these things, and the components might not fit them like a glove, like the Cinderella slipper every single time, but it doesn't matter. It doesn't affect the functionality of the footprint. So that's kind of why we can sit here and go, well, we can kind of pick something in the middle. And honestly, I think that would be fine to do in this case, because that way we're kind of centering the pad. That way in the case that we have a resistor that's a little bit shorter, then it will still be on the pad, and if it's a little bit longer, it won't hang off of it. So if we pick something roughly in the middle. So let's go with 1.45 millimeters plus Y, 1.45, and we're gonna pick the bigger one here. So 1.45 plus 1.4, that's 2.85. So we're gonna go here and we're gonna scroll down, find the location. Let's see where give me, okay, location is X right here. So I said 1.85, I think, or was it 2.85? 2.85, right? 0.85. Let me go back and double check my math on that though, just to be extra sure. So we had 1.4 plus 1.45, so that's 2.85. So boom, we're 2.85 millimeters away. So we're essentially done. This is the bare minimum that you need for actually creating a board that will work. However, we want to go a little bit above and beyond, and we want to make what I would say an aesthetically pleasing, professional looking footprint. And there are two major things that I want to add to this footprint to actually make it kind of look that way. So one thing is I want to put a little bit of ink on the top overlay. Just some, you can call it some guidelines. This will really help whenever you get your board manufactured, whenever you see these, it just helps you kind of spot them easily. And it helps you kind of in person when you're looking at the board, that it's sort of like a visor that way you can kind of match up because you'll have like hundreds of these little teeny, and these are small, right? These are millimeters talking here. So when you just see them, it kind of helps filter the chaos a little bit. So you can more easily spot your pads whenever you see this. So what I like to do is just draw 2 lines. I want to make them the length of the pads roughly. So I think we might need to constrain our snap grid a little bit, but I want to just pull it right to the edge of this solder mask right here. I mean, maybe we could actually, maybe we can go in a little bit, see what that is. Because one thing I've noticed too is whenever you're doing a nice, and we want to make sure this is, make that a nice straight line. One thing I've noticed is whenever these can become pretty annoying whenever you are trying to make a really tight PCB layout, and these giant lines seem to be getting in the way a little bit of you trying to place components next to each other. So that's like another thing to consider too. And don't worry, I'll show you what we can do about that, where hopefully it's not too much of an annoyance. But -1.5, just make that line just a little straight. That would bother me so much if I could tell it's just a little bit off. So did I say bring it into the purple or the red? The first one I brought into the red, and I want to copy that. Okay. That way it's not overhanging, like I said. That way if you're trying to make a really close and compact design, then these little lines aren't becoming, they're not doing more harm than good, so to speak. Let's make sure 1.25 is where it starts and ends. And again, we're good there. So I would say this is good. Another thing I want to do though is this is way too thick. Okay. We want to make it a little bit skinnier. Right? And now we can actually bring it in a little bit closer. And we will have to check, I think because there's a design rule that talks about silk to solder mask clearance, and depending on whether you can change it, whether it's within the footprint or not, but what I want to avoid is increasing manufacturing costs because the silk to solder mask clearance is too low. So basically what it's saying is whenever the solder mask is generated and they go in to do this, print this little layer, because this is going to be like in an ink type, imagine like a sheet of paper getting printed out. It's kind of, that's what this is, like writing and artwork. This doesn't really serve a functional purpose per se in terms of the electrical performance of the board, but like it still has like an aesthetic purpose. So, but it could cause problems that way, is what I'm saying, and lead to lower yield. This is the first major thing I wanted to put on here. So this again is starting to look a little bit better. Finally, though, the thing I want to add is an actual physical extruded 3D body, which is going to give us like a physical like piece to look at. And so looking at, that's when we're going to use this other piece up here. So here we're going to use all of these values here. So we're going to look at 1206, and we're going to scroll across here. The mass, that's really interesting, 10 milligrams. That's so tiny. So here we're looking at something that is approximately 3.3. We're going to take the biggest value we have, 3.3 millimeters by 1.75 millimeters. Okay. So what we're going to do is go to the mechanical layer, hit place, and it's going to be extruded 3D body. So this gets a little bit tricky, I guess, when you're drawing these things, because we're going to go, what did I say, 3.3 millimeters? And see, I might have to look back and remember. 3.3 millimeters by, what was the top one? Sorry, I have to look again. 3.3 millimeters by 1.75. Okay, that makes sense. 3 millimeters by 1.75. Okay. 3.3 millimeters. And then we got y is 1.5. Excellent. Okay, now we just make it a nice rectangle. I almost said square. Okay. And then 1.5. Okay, excellent. So then we right click. So then what we'll do is just drag it here. And this is when I would do something like edit, and I'll do set reference to center, and then it puts it at the center for me, and then I can just drag it right there. Easy peasy. The next thing I want to do is adjust the height of our physical component, and so that's going to be h, which is 0.55 plus 0.05, which is 0.6. So we click on this, and then it's going to give us the, what is it, no, it's the overall height, right? So that's 0.6 millimeters. Let me double check that value just to make sure I'm not. This is also to be extremely thorough when you're doing this, because you don't want to mess it up. It could really mess up your designs, and you're going to be using, because you're going to use this footprint over and over and over again. So it's important to get it correct. So if you're wondering what this actual mechanical layer does, what you can do is you hit View, 3D Layout, and boom, you actually get a nice little block. It looks a little bit like Minecraft, sort of, but still, this is plenty good. It really makes, whenever you're viewing your PCB in 3D, it really makes a huge difference. When you look at this and you see actual blocks as opposed to empty pads, it just makes it look a little weird. Like I'll open up, this is from that project right here, and if I hit View, 3D Layout, you're like, wow, it just comes to life when you can actually see the USB port and this stuff right here. So yeah, I think it makes boards look 10 times better. So yeah, that's pretty much all we need to cover for creating this actual footprint for a 1206 right here. I'm definitely gonna be doing some more footprint tutorials like this, because believe it or not, there's a lot of special cases or pieces of information that still could be valid by just doing a lot more of these. So I'll definitely be doing that. So but yeah, thank you so much for watching, and please drop a like and subscribe if this is helpful to you, and definitely it will help me to grow my channel if you do that. So pretty please, and thank you.